Welcome to the Wind Electric Systems section of Introduction to Renewable Energy. In this section, we'll be talking about wind electricity. Wind has been used as a source of energy for thousands of years to pump water, grind grain, and move seafaring vessels. Since the 1920s, wind has been used for the generation of electricity, and today it is the most valued of the wind's many uses. Wind turbines range in size from very small microturbines on sailboats to large utility-scale machines that are seen on wind farms. In the 1930s and 40s, hundreds of thousands of electricity-producing wind turbines were built in the U.S. They had 2 or 3 thin blades which rotated at high speeds to drive electrical generators. Then, by the early 1950s, the extension of utility grids to remote locations eliminated the market for wind turbines. Those people who had wind turbines at their homes were asked to remove them in order to receive a free connection to the grid. We'll discuss how wind electric systems work, system types, the basics of the wind resource, tower types, basic siting ideas, and barriers and benefits to wind electricity. So how do wind electric systems work? Let's look at wind turbines versus windmills. Oftentimes, people mistakenly call a wind turbine a windmill, or suggest that they want to install a windmill to capture electricity. These two systems are completely different technologies, and the difference is in the airfoil. Most people are familiar with windmills. A windmill uses a drag device, which is literally where the wind pushes the blades out of the way, creating a slow rotation speed and high torque. Torque can be used to do mechanical work, such as pumping water, sawing wood, or grinding grain. But drag devices, like windmills, can only move as fast as the wind's speed, which means that it does not have the ability to make meaningful electricity. In contrast, a wind turbine uses an airfoil to move. An airfoil doesn't cause a lot of drag and instead makes use of lift. This concept is the same idea as an airplane, kite, or sailboat. Pretend for a moment that a clump of air molecules are flowing toward the blade, or the airfoil. When it reaches the blade, that clump of air splits in half. Half of the molecules go above the blade and half go below. Because of the shape of the blade, there is more distance to cover on the upper side of the blade, so the molecules that went there separate more, creating a pressure differential. There is less pressure above the blade and more pressure below it, causing the blades to lift upward. The blades are attached to a central axis and spun in a rotational motion, taking advantage of the lift caused by the airfoil. The airfoil allows the blades to move at a speed greater than the speed of the wind, which creates a rotational speed that is better matched to the needs of electrical production. The area of the blades when they rotate is commonly referred to in the industry as the swept area. Just like a solar hot water collector or PV modules determine how much sun can be collected, the swept area of a wind turbine determines how much wind can be collected. The bigger the rotor, or the blades, the more wind it can collect. In talking about how wind turbines work, it is important to note that there are some very large differences in how small residential-sized wind turbines work and how large wind farm-type turbines work. Small residential-sized turbines are generally considered to be 1 kilowatt to 100 kilowatt systems. In a small residential-sized turbine, the generator is what converts the rotational motion of the rotor into electricity. The rotor is attached to one portion of the generator, either coils of wire or a magnet, while the other part of the quote-unquote generator remains unmoving. The effect is that the coils of wire are rotated through a magnetic field when the blades rotate. As we discussed in the first section, this would be an outside force that would make electrons in an atom want to react. When the coils of wire rotate through the magnetic field, it creates an electrical current. This energy created is used for the need of the home or business. On the other hand, large commercial-sized turbines that you would see on a wind farm along the highway works differently. A motor physically starts the rotor turning when a sensor tells the motor that the wind is fast enough to produce electricity. When there is not sufficient wind speed, the wind turbine will stand still. In a commercial-sized turbine, once the blades start rotating, they are kept at a steady speed, which causes the output to be grid-ready, exactly 60 cycle AC, which is the same as what comes through your sockets. This eliminates the need for inverters to match the 60 cycle AC before the energy can get passed along to the grid. In this animation, we're going to take a closer look at what happens when the rotor or blades rotate with the wind. Here we see that the wind must be blowing as the rotor is spinning in rotational motion. Beyond the blades, we can see that the magnets with the generator are also spinning with the blades. In the alternator, we can see a looping of copper wire that remains stationary attached to 3 conduits coming down from the base of the alternator. The blades will rotate, rotating the magnets within the generator. The wire coils in the alternator will fit right inside the generator and will be affected by the rotating magnets, knocking electrons loose and sending them down the 3 conduits, producing the 3-phase electricity that is produced by a wind turbine. For the rest of this primer, we will be talking exclusively about residential-sized wind turbines. The system types for a wind electric system is the same as for a photovoltaic system. We have grid direct, which as you may recall is the simplest type of system consisting only of a wind turbine and a DC load. We have standalone, or also known as off-grid systems, that like a PV system will be most likely when the utility power lines are not available, or if the owner wants to be completely independent from the grid. This type of system will require batteries and the maintenance that comes along with it. We also have the utility interactive system, also known as a utility intertied without battery backup, where the utility system acts as your storage capacity. And we have the bimodal system, which is like a standalone and utility interactive system rolled up into one. Just as PV modules need backup for when the sun doesn't shine, a wind turbine will need backup for when the wind doesn't blow. Wind is an intermittent source, and it will take a certain wind speed to cause a wind turbine to make useful electricity. This means that standalone systems are appropriate for remote power or on an application where you don't necessarily need power constantly. Or you'll need a backup generator of some sort. In order to fully understand how wind electric systems work, we first need to understand how wind itself works. As long as there is sun, there will be wind. Wind is a byproduct of solar energy. Approximately 2% of the sun's energy reaching the earth is converted into wind energy. The surface of the earth heats and cools unevenly, creating atmospheric pressure zones that make air flow from high to low pressure areas. Wind power is known as the measure of energy available in the wind. The wind power equation shows us the following. Wind power is equal to wind speed cubed. Think about that for a minute. Wind speed cubed. That means that if you were to double the wind speed that your wind turbine experiences, the available energy would increase 8-fold. So what does that mean for you? Well, there's one way that we can increase the speed of the wind that we experience, as Mother Nature has its limitations. We can increase the wind speed by building a taller tower. The higher the wind turbine is in the sky, the less obstacles the wind has to move around, which means the greater the speed in the wind. As we can see in this illustration, rough surfaces produce ground friction and turbulence that wreak havoc on the wind resource. When a wind resource reaches an obstacle, the wind itself starts to reverse flow and collapse on itself, trying to get all the molecules of the wind past the obstacle. Long after the obstacle, the wind is still attempting to redevelop its profile. These turbulent winds are not conducive to producing electricity. As a general rule, wind turbines should be a minimum distance of 30 feet above anything within a 500-foot radius. This would include buildings, trees, and anything else that could interrupt the wind profile. If you're in an area with dense vegetation or buildings, a new effective ground level is established at approximately the height where the branches of adjacent trees touch. Below this level, there is little wind that you can use, and it will have high turbulence, making most of the wind unusable for energy production. In order to lift the wind turbine high in the sky, we're going to need some sort of tower. There are 3 main types of towers, which are freestanding, guide lattice, and tilt-up towers. Freestanding towers are the most expensive because of their heavy metal needs. The freestanding tower is a dense lattice work of metal. It has the smallest footprint, but you have to climb them to do maintenance, checks, and repairs. This is the only tower type for larger wind turbines. Tilt-up towers have the largest footprint. They consist of a large pole, a gin pole, and guy cables going in different directions. In order to do maintenance, checks, and repairs on this type of tower, you have to tilt the tower down. Tilting the tower down is a lengthy and cumbersome process, but there is the advantage that you don't have to climb these towers, and in fact, you can't. Tilt-up towers are in the middle price range as far as towers go and come in limited heights. A guide lattice tower is the cheapest type of tower. In the looks department, it appears to be a cross between a freestanding and a tilt-up tower. It has a larger footprint than the freestanding tower, but less than the tilt-up tower. You must climb this tower to do maintenance checks and repairs. Wind electric systems have even more details that need to be taken into account than PV or solar water. There are a lot of different variables that need to be quantified and assessed. It is vitally important to get a site assessment done by a professional. A site assessor, as we know, first looks at the energy efficiency measures and is trained to know all of the considerations that would affect the production of the system you want. A wind site assessor, certificate holder, is trained to understand the average wind speed of a location, topography concerns, prevailing winds, and zoning issues in your area in order to determine the right type and size of system for the site. There are more barriers to wind systems than any other renewable energy technology. Some of these barriers stem from legitimate issues in the 1970s that people never seem to forget. In the 1970s, there were nearly 50 domestic wind turbine manufacturers, which was a reaction to the Organization of the Petroleum Exporting Countries, or OPEC, oil embargo of 1973, when energy prices were climbing and the federal and state tax incentives triggered a huge market. Unfortunately, at that time, not all of the manufacturers were good at what they did, and a lot of systems failed. Because wind turbines are so visible, being above the tree line, people saw these non-functioning, lawn ornament-like wind turbines and assumed that wind systems did not work. In the mid-1980s, the industry went through a major consolidation. The tax incentives disappeared, along with the energy crisis, relaxing the market. Today, there are less than a dozen domestic manufacturers, and they maintain a high standard. The National Renewable Energy Laboratory, or NREL, tests and rate turbines, and there is much out there in the way of checks and balances to make sure that turbines are working properly. As there is with PV and solar thermal, there is also checks and balances for the installation of wind turbines. Make sure when you start the process of installing a system that you are getting proven systems installed by experienced professionals. Make sure that your turbine has been tested by NREL and that you are using a North American Board of Certified Energy Practitioner, or NABCEP, certified wind installer, so you know that they have experience. Zoning can be an issue as well. Most cities and towns have ordinances to ensure that everything is safe and compatible with existing or planned development. Most ordinances don't name wind turbines by name. They have an issue with heights or other things required to have a successful wind turbine. Most restrictions occur in populated areas. Be sure that you or your site assessor checks the zoning issues in your community. The upfront investment for a wind turbine is a large barrier. Turbines aren't quite like photovoltaic panels in being modular. They are in a small degree where you can put up a tower and the wiring for the system you want to get eventually, and put a small turbine on it until you can afford the larger turbine. This is somewhat unrealistic as money will be a barrier to this method. In general, installing a wind system is one lump sum at the beginning. An important thing to keep in mind is that although a wind turbine requires a large initial payment, over its lifetime it will provide energy with no fuel cost while the cost of other sources escalate. A lot of the issues with wind systems can be labeled as NIMBY issues, which stands for Not in My Backyard. Among these issues are bird deaths, noise, ice, and aesthetics. In general, wind turbines are not a major hazard to wildlife. There have been bird deaths in a few areas of the world where large numbers of wind turbines were concentrated, and most of the recorded cases were due to planning errors where the wind farm was located near a nesting or migration area. But for the most part, single wind turbines don't kill birds in large numbers. Actually, the leading cause of bird deaths are buildings with windows. A cat will kill a significantly larger number of birds in its lifespan, which is about 10 years, than a wind turbine will in its lifespan, which is 30 to 50 years. By nature, birds will avoid wind turbines by flying around them, and migrating birds tend to fly above wind turbine height. Concern would be warranted in areas where birds concentrate, like wildlife refuges, feeding, or nesting areas. People are concerned about how much noise a wind turbine makes. In general, you may hear a small whisper of the blades or generator, which will get a little louder during low wind speeds. Turbine choice can reduce this whisper. A good noun to describe it, in my opinion, would be sound, not noise. The sounds that come from the wind turbine are so low that they hardly have an impact and usually become as commonplace as local traffic or the wind blowing through the trees. Some people object to wind turbines based on how quote-unquote ugly they think they are. Depending on where you live, wind turbines may be a relatively odd thing to see, so it's natural to get these reactions. There's really no way to deal with this issue other than to show your neighbors and officials what they are getting besides a quote-unquote eyesore is what a wind turbine means for the local economy and the other benefits that come along with it. There are many other NIMBY issues that can and likely will come up during a meeting or zoning committee. People tend to fear the technology, and so they will come up with concerns about it. Issues that have come up in the past include wind turbines cause ovarian cancer, they interfere with televisions and radios, etc. These, of course, are false, and there are likely local wind advocates that you can get in touch with to help dispel some of these myths during a zoning committee meeting. Misinformation is definitely the largest barrier to wind. People get wrong information or have unrealistic expectations, then tell others that wind doesn't work. Wind does work, but like all other technologies, it has its limitations. Wind is not a baseload generating technology, which means that the wind doesn't always blow when you need it. There aren't always transmission systems where the wind resources are the best, such as some of the less populated plains states. The benefits of wind power include some obvious environmental benefits. A utility-scale wind turbine avoids producing 10,000 tons of carbon dioxide annually that would be produced by burning coal. Towns, counties, and landowners benefit directly from the installation of wind turbines. There's job creation and the money that isn't going to be exported for resources out of state. That's it for this section, but if you want to know more about wind electric systems, you may want to check out some of our other courses. Two courses that may be of interest are W050, Primer on Wind Electricity, or W101, Introduction to Wind Systems. If you're interested in installing your own system, you'll want to have your site assessed by an MREA Site Assessor certificate holder. You can find the list of site assessment professionals at www.mreacsa.org. In the next section, we'll be discussing other alternatives including biomass, biofuels, hydro, and geothermal systems.